Hey gamers, today we're going to learn Taylor polynomials. We'll use e to the x, centered at x equals 0. We'll use e to the x for this. The derivatives will just be 1, since all the derivatives are the same of e to the x. And so make it pretty easy to just see the patterns. So we'll start off by just making a tangent line. In this case, it'll just be x plus 1, since the slope is 1, and it's a value of 1. And that gives a pretty good approximation for a bit, until it eventually starts diverging, because it'll have the same slope. If I make this g to the x, and we compare f prime of x, g prime of x, one is a constant, and the other is an exponential function. So they start getting different, and this creates problems. So if we can make it so that their slopes stay the same for longer, then we can make it so that the approximation is better, because then they'll take longer to diverge. And just like how using the derivative made it so the function were closer together, we can do the second derivative to make the first derivative closer. So as mentioned, all the derivatives x equals 0 will just be 1. So then we should just use x squared, and then they'll have the same derivative, and it'll be great. So let's see. I go like x squared plus, and that's not what we expected. Why did it not do that? Well, it's because x squared, second derivative, is 2. Because of power rule, you gotta bring the exponent out front. So to deal with that, we need 1/2 x squared. And now, we successfully have an approximation for the derivative. But just like our original function, this also eventually starts diverging. So to make the approximation better, we need the derivative of the second derivative, the third derivative. And once again, we need this third derivative to be 1. And if you think about how x cubed would work, because we already use x cubed, that by the time you reach the third derivative, you have done 3 times 2 times 1, 6. So we will need 1/6 x cubed to approximate this. We get the third derivative. And now we got approximation for the second derivative. And by the way, just to make sure it's clear, the reason why we can use each polynomial term without affecting any of the other terms is because we're centered at x equals 0. And if you think about it, for any polynomial term at x equals 0, it will only have an effect for a single derivative. The constant will only have an effect during the original function, because during any derivatives, it's gone. It goes to 0. During the original function at x equals 0, this is 0. This is not doing anything. All of these are 0 inside the original function. So they don't do anything. And so the first derivative, these are both still 0, because this would be 1/2 x squared, and that would just be plus x. So this is the only term, this would be plus 1 instead of first derivative, that actually has an effect. And we go to second derivative, and because this was a constant, it goes away. So now all we have is these two terms. And this one, but that's still 6x. This term is still 6x, so it's still 0. But this one would just be 1. So it's having an effect there. So during taking each derivative, only one polynomial term will have an effect, because it will either have an x on it, which in anything times 0 is 0, or it will reach a constant, and then it's having an effect, and after it reaches that constant, and it's a constant, and the derivative of that is 0. So we could keep going with this, but I think you see the pattern that's going on here. For each term has to be one exponent higher than the last. Specifically, due to power rule, subtracting the exponent by 1 for every single derivative, after n derivatives, the exponent will be decreased by n. So if you were to have an exponent of, let's say, x to the 15th, after 5 derivatives, that would be x to the 10th. So if you want it to be a constant, then you need to do n derivatives. So x to the 15th, once again, after 15 derivatives, will just be a constant. And specifically, it will be the factorial of 15, because it will be in a 15 from the, because it'll have that 15 from the first derivative, then times 14, times 13, times 12 from each derivative onwards after that. So we get this general idea that in order for the f to the n derivative, basically, f to the n term, we want it to be that. This general idea that I want to use the f to the n derivative at that point, in this case 0, and we want it to divide it by the factorial of n. We cancel out that power rule, bringing out the exponent every single time. Let me rephrase that. We want to divide by the factorial to cancel out the power rule, bringing down the exponent every single time we do it. Just like how with x cubed, it wasn't just the third derivative of x cubed was 1, it was 6, because it was x cubed, and then 3x squared, then 6x, and then 6. And then basically, we want this to be a constant at that point, because if it's x to the first, that's going to be 0 to the first. And if it's x to the second, that's going to be 0 to the second. That's all just going to be 0. We need it to be a constant at that term. And as soon as it's a constant, it's gone. So it only affects that term. Now, so far, I've only been doing this at 0, which is technically called a Maclaurin series. Excuse my pronunciation. However, you don't have to center it at 0. Let's say instead we centered it at 1. Well then, we still want it to be that term only has an effect when it's a constant. So if we're doing with x equals 1, then in order to make that 0, we need to subtract 1. So if we're doing with x as c, then we can assume we're doing x minus c. Just like I said a moment ago, like if we were trying to base this approximation at 1, then we would have to do all the derivatives based upon that x equals 1. Based on x equals 1, we also have to subtract 1. So that way, none of those terms. That way, each term only has an effect while it's a constant. That way, during every other term, the x minus c is 0, and that term gets zeroed out. So let's see this. If I do this here, let's see here. Both for just like before, all the derivatives of e to the x are the same, and specifically at 1, e to the first is just e. So all the derivatives at x equals 1 will just be e. I guess this will just be e to the x, this will be e over 6, and minus 1, and e, minus 1, e, minus 1, and finally, let's see. And look at that, now our approximation is centered at 1.